microscope. For today's talk, we have Sarah Mikula. Sarah Mikula is the lab manager here at CEMAS, so she takes care of the lab, make sure things run very smooth that way. Does a lot of bio prep. It's more recently been doing quite a bit of work on the CT as well. Sarah did her education at the University of Oregon before spending a few years down in California at UC Davis. After being out there for a few years, she moved out to Germany for, she said originally it was going to be there 2 years, ended up being 10. So she clearly enjoyed her time out there, got a lot of work done. So she's at the Max Planck Institute working to map neural circuitry using scan block face electron microscopy. So that brings back a lot of natural stuff into electron microscopy. She came back to, or she came to Ohio initially at CMIF to do work with them. And then after being there a couple of years, came over to CMAS to kind of work on the microscopes with us here. So it's been great having her here for a couple of years, doing a lot of bio work and doing some other work as well. So she'll be talking today about multiscalar imaging between microCT and electron microscopy.
Thanks, Dan. As Dan said, I'm Sarah Mikula. I know all but one of you, and I won't point that out. As Dan said, I'm the lab manager and the safety officer. And earlier this year, I became the Heliscan instrument manager. My background is in mapping neural circuitry, and I don't want to give that up, even though nothing that I do now directly relates to that. So whenever anyone brings me a brain sample, I get really excited. Let's see. Okay. I apologize if this is a bit blurry. I think it looks okay. Electron microscopy is great. I know that we are at the Center for Electron Microscopy and Analysis, so you all know what electron microscopy is, but I do want to just start with the very basics. Electron microscopy offers us the ability to image samples at very high resolution. And I would argue that it is better than light microscopy for this, although there are some techniques using light microscopy that can at least rival electron microscopy in terms of resolution. But there are limitations to that. So first I want to convince you that electron microscopy is really useful. And then I want to go back up the arrow and talk about how we do need large scale context. So the advantages of electron microscopy over light microscopy: higher resolution, and also dense morphological visualization. So when you use light microscopy, you often rely on fluorophores or tagged molecules or antibody staining or something that's going to tag your feature of interest. And the rest of the sample looks dark. But if you want to, for example, reconstruct a neural circuit or any large piece of tissue, then you need everything stained. You need to be able to visualize everything. And this is an example from a publication that used CLEM, and I think it shows this very, very nicely. I don't want to mess with my cursor because I can't track it or see it, so I'm going to walk over here and point it out. So in this image, we have a fluorophore that has stained a neuron. And you can see that neuron, but the background looks dark. If you use DAB, it will precipitate on this fluorophore, so it clearly marks the cell of interest. And now you can see the context, now you can see everything around it, which is important because if this is the cell that has that DAB marker, we can see vesicles and synapses that form connections with that cell. So it's necessary to not just have high resolution of the one particular thing you want to see, but also to be able to visualize what's around it. A word on electron microscopy. I am a fan of scanning electron microscopy. I know that not everyone shares this view, but I love it. So I took these images. I had a piece of tissue stained with heavy metals embedded in resin, and I sectioned the sample. And on the right, you can see the section that I took imaged in TEM. And on the left, you can see the sample in the block face imaged in SEM. I would argue these are comparable. So let's go back to why we care about electron microscopy. Okay, we get really high resolution with electron microscopy. Electron microscopy gives advantages over light microscopy, but light microscopy has that blue arrow that goes further to the left. So if we have an electron microscopy data set and we take really high resolution images and a whole bunch of them, that data set soon becomes unwieldy. It gets really large. We end up spending a lot of time and resources collecting data that we don't always need. So this is why microCT is a really nice method to combine with electron microscopy. And I'm going to show you the compatibility of the two, but this covers, pretty soon we're not going to need light microscopy at all. Kidding, it's still useful. X-ray microCT is like shadow puppets. So you have a sample, which is analogous to your hand. You have an X-ray source, which is analogous to the flashlight. And you have a detector, which is analogous to the wall. Same geometry. If you want a bigger shadow, move further away from the wall, move your sample further away from the detector, or get your sample closer to the detector, bigger shadow, better resolution. It's the very basics of microCT. You do get three-dimensional information because the sample will rotate, and the images collected are then processed to be reconstructed, and it results in a TIFF stack that you can fly through. And I will show you one of those. But before I show you one of those, on the left, you see a two-dimensional image from a microCT scan of unstained mouse liver in a centrifuge tube. The circle is the plastic centrifuge tube. In the middle, you see a piece of liver that's been stained with osmium tetroxide, which is a very conventional heavy metal stain used in preparing samples for electron microscopy. On the right, you see a sample that's been stained with iodine, which is cheaper and penetrates more readily than osmium tetroxide. And this is another talk. But the point is, you can see more features in the middle and right sample than you can on the left because it's been stained, the contrast has been enhanced, and you can tell that the contrast is brighter because the centrifuge tube is actually the same density in all three images. It's just the one on the left shows up brighter because the images are normalized. So I'm going to, good. So I had a user take a look at mouse aortas, mouse heart valves. And she had some extra samples, so she let me keep one. And this is a microCT scan through one of them. It's very nice. It was heavy metal stained. I stained it with ROTO, which is reduced osmium thiocarbohydrazide osmium, because I knew I wanted to image it with electron microscopy. So that was why I didn't do it the cheap, easy way. That middle image is one of the frames from the fly-through that we just looked at. And I like this particular frame because I cut into the block base and smoothed it and imaged it in SEM, which is the image that you see on the right. And I can match that. I can find that plane so I can correlate the microCT data set to SEM. So, oops. Quality control check. So this is the same image on the left that you saw on the previous slide. And on the right, it's just zoomed in to that center feature. I could have zoomed in more. I can see cell nuclei in this. I could see subcellular organelles. And if I wanted to take a section from this block base and look at it in the TEM, I could probably get even higher resolution. So lots of possibilities there, but this is only to show that the sample preparation that enhances contrast in microCT also enhances contrast in EM. They are compatible. I really like this. I recently won a grant to explore different embedding media. On the left, you see two samples. I've simply glued them together nose to nose. Both of them are mouse heart tissue. They've been stained. Both of them are embedded in conductive resin. The one on the bottom is embedded in colloidal silver epoxy, and the one on the top is an organic conducting polymer that's been suspended in epoxy resin. And in the bottom sample, it's fine. You can effectively find where your sample is. You can't really see any features, which when when the block is opaque and you can't find your sample at all, that's enough to hit your sample if you want to image it in EM. In the top, you can actually pick out which ROI you are interested in, trim the block down to that, and then image it in SEM or TEM. I'm really excited about that top block, actually. There's more work to be done on that. So, very short talk, but microCT is extremely useful as a preliminary step for electron microscopy. It's compatible, so you can do multi-scalar imaging starting at a large scale and zooming into a small or a high resolution small scale. You can localize ROIs if your embedding material is opaque and you otherwise cannot find your sample. It's also, I didn't show this, but just simply reasoning through, it's useful if you have a sample and you aren't sure if it is undamaged throughout. And it's a really nice way of preventing wasted resources, let's say, because electron microscopy takes a lot of time for staining and all the manual labor that goes into it, and then imaging time, and then storing the data and analyzing the data. And it's a shame to go through all that and then find out that your sample was bad. On the right is an image of a buckeye collected in microCT because we are at OSU. That's the end of my talk. If you have any questions, let me know.
Thanks, Sarah. So if there's any questions in the room or online, if you're online, feel free to post those in the chat or the Q&A. In person, go ahead.
Yeah.
When you're combining to start this,
so what I would advise really is how I start almost every question, like what's that for my experiment? It depends on what you want to see. If your sample is homogeneous and your method is reliable and you're confident that it's going to be the same throughout, you don't need to do this. Unless you want large scale context to show zooming in on whatever it is you want to image in. But if you're not sure, yeah, it's a really good idea. And also the helioscan at CEMAS right now is quite cheap to use. So it's a nice use of resources.
But I mentioned that but like how small you can get or small you can get.
Great question. 800 nanometers with an ideal sample on a good day. Yeah. Yeah. It's pretty good. It does require a small sample that can be very close to the source. So that's like really ideal. Usually people are looking in the range of 1 to 10 microns for their pieces of interest, which is a pretty good starting point if you want to do further. Okay. The sample you detected?
Yeah.
Yeah.
Which one, like this sample is smaller, you get better resolution?
So it's the same as
Thanks, Sarah. Could you repeat the question for those online?
Yeah.
Here.
The question is about the how the resolution changes depending on the proximity of the sample to the detector. It's the same thing as a shadow puppet. So if I have a flashlight, there's a flashlight, it's shining like that way. And this is my sample. It's my shadow puppet. It's going to make a dog on the wall. If I get closer to the wall, I get a smaller shadow. So if I move that wall or that detector further away, then the shadow gets bigger and my resolution improves. Which is sometimes counterintuitive, but then when you think about it in terms of a shadow, it becomes more easier.
Question on the heart valve.
Yeah.
So if you go back to those two, there was the SEM and the CT image. It looked like near the top part was missing, or the top left part of the SEM image.
Oh, I see what you mean.
Cutting,
yeah. So the question is, why does the SEM image have this little white rectangle on top? This is because I trimmed the block. It's a resin block, and I trimmed the edges of it away. So that edge is not in plane with the focal point.
Does it off axis a little bit then?
I think it is, yeah. Or it's debris or something. Yeah, sorry if I got too loud there. But that's one of the wonderful things about SEM block-based imaging. If your block base gets messed up, you just smooth it again and take a look.
How long did it take you to collect that?
The microCT data or the whole thing SEM included?
Well, not the SEM, just the
2 hours. I mean, the setup time was a half hour. The machine ran for 2. That's another reason I love the Heloscan. You can set it up and then you walk away and then you come back and you have data.
So after you collect the data, how long did it take to analyze the data and then also prep?
So I would argue that analyzing the data is what we're doing right now. So let's factor in this time. Creating that took about 3 minutes. I dropped the TIFF stack into ImageJ and I flew through it and saved it as a .avi. And that was it. So it was one of the most user-friendly machines I've encountered. It's wonderful.
If you want something for the cover of Nature, that takes a little long.
Yeah, you have to color it.
Yeah, so it's first doing microCT, then all sample prep stuff, all sample prep take.
Sample prep is the same as EM. So I prepared the sample as if I were going to image it for EM. So I did the heavy metal staining and the resin embedding, which is that can change, but it's conventional EM processing. It can take 3 hours, 5 hours. You have to allow the sample to sit in a heavy metal and be stained. And then it takes an overnight step or 2 to allow the resin to infiltrate. But it's not like you're working solidly at it for 2 days. It has a lot of wait times in it. That would be the same with or without microCT though. So that's regular EM processing. I didn't do anything extra before imaging it in microCT. I just took that resin block, imaged it, smoothed it on a microtome, and imaged it in SEM. So if anyone wants to use a Heloscan, let me know. It's pretty great. Yeah.
How do people prepare for, like, if they run an image metal or like grain, not grain, like how do they prepare this?
They just bring it. A lot of people just bring a piece of metal. Yeah, it has to be mounted on a post, so we'll super glue it to something or stick it in some foam on a post, but there's nothing that needs to be done in particular.
Someone was asking about what KB was used to collect that image data for the CT scan.
Oh, I have it written down. I didn't include it here. I think it's either 80 or 100 KB. Great. Well, thank you. If you have any further questions that you think of later, let me know.
Thanks again, Sarah, for the talk. If you're here in person or online, you can join us for a coffee hour next. We're gonna go finish up the donuts, drink coffee, that kind of thing. Or be on the scope once a month. Next month is going to be XPS. So yeah, it's gonna be over the main campus to talk about XPS and hopefully some correlation with SEM as well that we've been able to do. And then the month after that is gonna be doing RKD in SEM. So I'm working with Thermo on developing a new detector. We'll talk about that a little bit start of December. Okay, see you guys next time.
Yeah.